Hello, welcome everybody to the second session of IoT Semantic tutorial. Today, myself, Andrea Cimino, and Bob Flint will present this tutorial. Hello, everybody. My name is Andrea Cimino, and today, along with Bob Flint, we are going to present IoT Semantic tutorial part 2, using semantics in an oneM2M deployment. Today's agenda is this one. First, we will review some essential material from the part 1, basically ontologies, the SAREF ontology, SPARQL, and oneM2M resources. Then we will check out what we can do with the oneM2M based ontology. We will have a use case description, and then we will address the ontologies that support our use case. Finally, we will have a review of the deployment architecture for this use case that we will have described before. And finally, we will have a control application using semantic queries. So let's start from the review. In the first part of the tutorial, 3 main technological pillars were explained, namely OWL, RDF, and SPARQL. These 3 technologies are standards from the W3C and are conform part of the semantic web stack technology. Let's start reviewing the first one, the OWL, which is the language that implements the ontologies. The ontologies are a formal specification that define a model to express RDF data. They are implemented using this vocabulary called OWL, that is a semantic web language designed to represent rich and complex knowledge about things, group of things, or relation between things. Currently, we do not need to develop from scratch a new ontology when we want to start using one. Instead, there is a large corpora of already developed and published ontologies following the W3C standards and the good practices for the deployment and development and publishing, which are also being standardized already. And this is the case of SAREF that we will explain later on. Basically, the takeaway for the ontologies is that they describe a data model that we can use when we are going to express data following the RDF format, which is, by the way, the next technological element we are going to review from the first part of the tutorial. RDF, which it's an acronym for Resource Description Framework, is a W3C standard to express data. The way it works is that data is somehow described using this standard, but then it can be serialized in different formats. So you can have RDF data expressed in XML, or in JSON-LD, or in Turtle, or in Ntriples. There are a lot of, or at least quite a long list of serializations. And all the data in these serializations can be translated into another, and the data will be the same. The only thing that changes is the format, is the syntax of the data. But the key point, the bottom line, is that the semantics of the data remains the same. Finally, the data expressed in RDF must follow the restrictions defined by an ontology. Although it is true that someone can write and express data in RDF without following an ontology, that is not a good practice, because nobody will know which model the data follows, right? So what it should be done is take an ontology and express the RDF data following the model, the definition, and the restrictions indicated in that ontology. And in this slide, you can see an example of a lamppost that is expressed in RDF, in this case using the SAREF and SAREF for Envy and GeoSPARQL ontology. And you can see in the front box, data expressed in Turtle, and in the box in the back, the exact same data expressed in RDF. So as you can see, the data and the syntax remain, the semantics remains the same, although the syntax in both boxes is different. Now, When we have all this data expressed in RDF, we need to somehow query this data. And for that, the W3C has proposed the SPARQL query language, which is used to express queries over RDF data. SPARQL is a standard that has several documents. It's very complex, but to sum up the SPARQL recommendation, SPARQL is split in two types of queries. One type for fetching data and the other one for updating data. In this review, I'm going to focus only on the types of SPARQL that fetch data. And for those, we can differentiate two types. Select and ask, which basically return a payload that can be expressed in JSON, XML, or CSV. And they allow you to make queries over the data. And then we have the construct and describe queries, which return RDF. So the first one are used to somehow filter the data, and the second one to build RDF, taking the already existing RDF into account. And here on the corner, on the bottom corner, on the right side, you can see an example of query. In this case, and for this tutorial, we are going to focus only on select queries. And you can see that they have a fixed structure. First, we need to specify the prefixes. This is not mandatory, but it's something optional, but leverages the effort of writing the query. Otherwise, we will need to write full URIs for the properties, which is a bit verbose, maybe. So we define these prefixes, then we say the type of query we want to use, select in this case. Then any word that has a question mark at the beginning, it's a variable. So in this case, we specify that we want to get back from the RDF data to variable, street, and smart object. Where, and now we put the clause where, and we start indicating statements that have restrictions. Statements are triples, okay? And each element in the triple, it can be a subject, predicate, object as RDF. And when we specify something with a question mark, as I mentioned, it will be a variable. And when we do not specify something with a question mark, it will be a restriction. So for instance, our first statement is street, which is a variable, GeoSPARQL SF contains, which is a constant, and smart object. This means we want to retrieve anything that has the property GeoSPARQL SF contains, and the object of the triple is anything, okay? And the next statements are similar. We have smart object, a SAREF type. It means that any smart object that is in the range of the property SF contains has the type SAREF sensor and also has the type SAREF device. This is a very quick catch on the standard. For further details, we really recommend checking our first tutorial, which explains more in details these technologies.
Also, in part one, we talked about oneM2M support of semantics. In particular, the types of resources or attributes that oneM2M has in order to contain some of the semantic functionality that Andrea was just talking about. So a couple examples are the ontology reference resource, which contains a reference ontology that holds that formal description of a semantic information and explains the meaning of the data that would be present in the semantic descriptor resource. And then also the semantic descriptor resource, which contains all the RDF triples that describe the device or the resource that we're modeling. The format of the triples, as was mentioned, there are many different formats that are supported, by SPARQL and the W3C standard. Well, also in oneM2M, several of those formats are also standard or are allowed for the specification of the semantic triples, and I'll describe that. So as another example of the semantic triples that would go into a semantic descriptor resource, what I'm showing here is an example of the RDF triples that would describe a light post. And what we had talked about in part one was we can describe things like what the device is, what the device does. We can describe the location of the device or where it is. And we can provide other useful information such as a manufacturer information or last maintenance date. And we can also describe properties of the device, or in this example, it's properties of the light. In oneM2M, in order to transmit that semantic descriptor or those RDF triples, we put that into a semantic descriptor resource, and then we send that just like other oneM2M resources, in a primitive with a semantic descriptor resource payload. Now the format of the semantic descriptor payload is specific and requires a little bit more work than some of the other resources in oneM2M. So as we mentioned, there are several different formats that the triples can be described in, and in TS004, we have a list of the supported formats that oneM2M will acknowledge, and that value gets represented in the semantic descriptor resource. And then also in the semantic descriptor resource is the attribute for the descriptor. And this is the attribute that contains the RDF triples. Now, when we put the RDF triples into the descriptor attribute, we have to take all that text that we saw in the previous slides, and we have to put that into a base 64 binary format. And that's just a matter of running through a well-known standard algorithm, which I'll show you during our demonstrations later. This is a quick representation of a semantic descriptor resource and the payload to perform a create of a semantic descriptor resource. So as I mentioned earlier, the format is specified. In this case, the DCRP is the descriptor format, and that's a 4 which evaluates to XML. That was the format used in part 1. And then in this DSP attribute, which is a short name for descriptor, that's the base 64 encoded text that I showed you from the sample earlier. So also in part 1, we talked about how to send a semantic discovery request. And earlier we showed an example query, and what we need to do with that query is we need to, for the HTTP protocol, we need to do the percent encoding of it and include that query in an attribute, the semantic filter query, SMF. And that all goes into the query parameter of the HTTP request. Also, we have to set the filter usage parameter to discovery. So that's the FU equals 1. And then also set the to parameter to scope the discovery search. So in this example, I am showing you the scope is at the CSC base of the request. So it's at the top level, and it will include all of the semantic descriptors that the originator has permission to access. Outside of this, all the other parameters and procedures are the same as oneM2M primitives, and it's pretty straightforward. So what we're going to do now is talk about what we can do with the oneM2M base ontology. What we just completed is the background information necessary from part 1 of the tutorial, and that was a brief summary in order to make sure that we all understand the components, the basic components that we're going to build upon in the rest of this presentation. Semantics provides the ability to have syntactic interoperability of devices and applications. And using semantics, an application can be written such that it knows what oneM2M resources and operations can be used to interface with the device. And also, we can write applications that know what values to use when interfacing with the device. And this addresses a big issue in Internet of Things. In order to take advantage of devices or resources that are out there, we have to know what the APIs are for those devices, and we have to know how to interact with them. And the oneM2M base ontology provides that information. So, here I pose a question: how do I turn on the light of a street lamp? And the answer to that is I want to create a resource. It's going to be a content instance resource with the payload on, the value on, and the target is going to be my CSE base, this device name, and light command. And what we'll see later is how we can get all this programmatically and not require human intervention in order to get these answers.